Welcome to Plutus IAS, and today we are covering spinel oxides. So today in our discussion we will discuss what are spinel oxides, how they are formed, and how can CFT explain how the oxide formation of the spinel occur. Now the thing is, spinal oxides, before the existence of CFT, we cannot predict how the particular type of compound exists, how it is forming, and why, if any kind of distortion that is occurring in the structure, why the distortion particularly exists. So CFT came in the existence and it help us to explain the existence of spinal compounds. So at first, what are spinal oxides? So spinal oxides are our mixed metal oxides. By mixed metal, I mean here that the mixed metal here is in terms of oxidation state. That whatever the metal that you are having, they have different oxidation states. In spinal oxides, they are generally represented by the type M3O4, where metal exists in two different oxidation states. One is a 2 plus oxidation state and the other one in 3 plus oxidation state, and you have 4 oxide ions. This is a general configuration of your spinel. Now, these M2 plus ions are found to be exist in solid state in the CCP lattice, which is formed by the oxide ions, which are also our weak field ligands. And then we have M2 plus ions, which are present in the tetrahedral voids formed by this CCP lattice, and N3 plus ions in the octahedral voids. If this type of configuration we are getting, that all the M2 plus are in the tetrahedral void and all the M3 plus in the octahedral void, then such kind of oxides will be called as your normal spinels. But if there is a distortion, that means some of the M2 plus are now have moved to the octahedral voids, while some of the M3 plus have moved to the tetrahedral voids. If this behavior is observed, then we'll say that the oxide that we have got is a inverse spinel. So, for example, if I say, if I give you a compound, let's say of type Pb3O4, can we call this an spinel? Well, the answer is absolutely no. Why? Because the Pb here exists as 2 plus and as Pb4 plus. But for spinel, we require this Pb to be in at least in 3 plus oxidation state. But since they are being separated by two different oxidation states, hence this is not a spinel. Now, how CFT explains the existence of spinels when they are getting to be formed, when we can say that the oxide that we have, it is a normal spinel, or when we can say that it is an inverse spinel. So what does CFT explains? CFT brings in the concept of that if M2 plus is existing in the tetrahedral void, it compares the tetrahedral void like the tetrahedral splitting as per CFT, and the M3 plus which exists in the octahedral void, it assumes that to be splitted similarly just like in the octahedral splitting as per CFT. So let's try to explain as per a given example how this can explain the existence of the type of spinel. So if I take Mn3O4, I can write it as Mn2 plus 2 Mn3 plus and 4 O2 minus. Now, if I assume this to be a normal spinel, then M2 plus would exist in the tetrahedral voids and Mn3 plus will exist in octahedral voids. But if it is an inverse spinel, some Mn3 plus will exist in octahedral void and some Mn3 plus will exist in tetrahedral void. So I need to find the CFSE for both the cases. So Mn2 plus is D5 configuration, Mn3 plus is D4 configuration. In tetrahedral voids, I can write it as, in tetrahedral void, the electronic configuration will be T3, T2G, EG, not sorry. In tetrahedral void, it will be E2, T3, where it has the CFSE equals to 0. And in octahedral void, it will also have CFSE equals to 0. But in case of when Mn3 plus is present in tetrahedral voids, the electronic configuration we have is E2, T2. So in T2, in E2, the electron we have charge of -4. It has a charge of -6 with 2 electrons there plus 2 electrons in the T2 state, which has plus 0.4 contribution of CFSE del O. In case of octahedral void, it is T2, G3, EG2, and the CFSE sorry, this will be tetrahedral. So the CFS, it will be given as 3 electrons with minus 0.4 contribution del O plus 2 electron with plus 0.6 contribution of del O. So if you are thinking that Mn34 is a normal spinel, that the total CFSE should be in plus of tetrahedral void plus of the CFSE of a Mn3 plus void. Now, if it's a normal spinel, the Mn2 plus will have 0 CFSE, while Mn3 would be present in the octahedral field, where I can write it as minus of 1.2 del O plus 2, 6, 12, wait there, T2G, T2G3, 3.4, total 3.4 minus 3, 4s are 12, 1.2, 2, 6, 12. It for octahedral it is should, yes, sorry, it will be 0. It will be 0. T2G3 for the CFSE normal, Mn2 plus will be in tetrahedral voids. They have a configuration of 0 plus. CFSE in the octahedral void would be also 0, while the CFSE in the normal for the inverse spinel will have Mn2 plus in the octahedral voids. In octahedral voids, the CFSE will be again 0, but when Mn3 plus is in the tetrahedral void, it will give us a value of, wait, if I solve it, it will be a total of minus 1.2 del O, minus of 1.2 del O. In case of inverse spinel, I have 4 electrons. 4 electrons as per E2, T2. I can write it as 4 electrons with minus 0.6 contribution of del T, and if I convert it 4 into 4 by 9 times of del O, this value will serve out to be minus of 1.8 del O. Remember, since these oxides are present in different splitting environments of tetrahedral as well as in octahedral, so here we did the conversion to convert the tetrahedral splitting into octahedral field type. So here we can see that the CFSE for a normal spinel came out to be minus of 1.2 del O, while which is greater than the CFSE for the inverse spinel. Since CFSE is a stabilizing factor, we can conclude that this, as per this, the Mn3O4 is nothing but a normal spinel. Okay, so with this we have figured out how CFT helped us to explain when the oxide that is being formed is a normal spinel or when we can call it as inverse. One exception exists for this case, that we have cobalt 3O4. Cobalt 3O4, as per CFT, it should be a inverse spinel, but this is wrong. In actually, CO34 is a normal spinel. Remember, this is an exceptional behavior. It is not an inverse. CFT makes wrong prediction regarding this particular type of oxide. So I hope this would have cleared all of your doubts. In case any other further queries, you can add it to the comment section and we'll get back to you. Okay, thank you for joining us for today. That's all for now.